Least common mechanism. Minimize shared components. Opening. The wall that was never there. Picture a large apartment building. 50 families, 147 people living independently. Each has their own front door, their own key, their own private space. But they share the lobby, the elevator, the boiler room, and the basement utility corridor. Now, imagine that a thief breaks into the boiler room. From the boiler room, there's a maintenance passage that connects to every apartment's gas shutoff, every electrical panel, and every water supply. The thief did not need to pick 147 locks. They needed to pick one. The shared utility infrastructure was the attack. This is the mental model of least common mechanism made physical. In a building designed correctly, the shared mechanisms are as few as possible. The gas shutoff for apartment 12 does not physically connect to the gas shutoff for apartment 47. They share a street-level feed, perhaps, but from the meter inward they diverge. Each apartment carries its own dedicated branch. Compromising one does not give access to the next. The attack on the boiler room is contained. Now translate that building into an information system. You have applications running on shared servers, users authenticating through shared directories, microservices calling each other across shared internal networks, tenants in a cloud environment sharing the same physical hardware. The equivalent of the boiler room exists in every one of these designs, in its specific form, which shared component, at which layer, serving how many users or processes, is the thing that determines whether a single breach becomes a contained failure or a cascading disaster. Least common mechanism does not say that sharing is wrong. Shared components are how modern systems achieve scale, cost efficiency, and consistency. What the principle says is that every shared component is a risk that must be consciously chosen rather than incidentally accumulated. The question it demands you ask about every design decision is this: does this component need to be shared, or does it need to serve one user, one process, or one tenant in isolation? And when sharing is genuinely necessary, what is the smallest scope of sharing that still delivers the required function? That question, applied consistently across every layer of a system, network, compute, identity, data, application, is what separates architectures that contain failures from architectures that propagate them. This session is about understanding that question at every level where it matters, and about the operational reality of what happens when the answer was wrong. The principle and its vocabulary. Before the mechanics of isolation can be discussed, the vocabulary needs to be precise. Least common mechanism is one of 8 security design principles articulated by Salzer and Schroeder in their foundational 1975 paper on the protection of information in computer systems. It sits alongside principles you may know better: least privilege, economy of mechanism, complete mediation, and it is the one that is most commonly violated not through negligence, but through the entirely reasonable desire to build efficient, centralized systems. The word mechanism here is deliberate and important. A mechanism is not just a piece of software or hardware. It is any component of a system that mediates access to a resource. An authentication system is a mechanism. A network switch is a mechanism. A database connection pool is a mechanism. A message queue is a mechanism. A shared file system is a mechanism. What all of these have in common is that they sit between a user or a process and the thing that user or process wants to reach. They're the middlemen of system access. The principle says Minimize the number of these middlemen that are shared across different users or processes. When the same authentication service handles both the payroll application and the public-facing customer portal, a compromise of that service potentially exposes both. When the same database connection pool serves both the reporting module and the transaction processing module, an error in one may corrupt or expose the other. When the same network switch handles traffic from the development environment and the production environment, a misconfiguration in one may allow traffic to cross into the other. Shared mechanisms create what security architects call pivot points. A pivot point is a location in a system where an attacker who has gained access to one thing can gain access to another thing without acquiring a new credential, exploiting a new vulnerability, or crossing a new trust boundary. The pivot is horizontal. It moves sideways across the system through the shared structure. The classic expression of this is lateral movement. An attacker who compromises one server on a flat network can reach every other server on that network because the shared network infrastructure offers no resistance to the sideways travel. The network was designed to facilitate connectivity. Lateral movement is just connectivity being used in a direction its designers did not intend. The distinction between the isolation that least common mechanism demands and the isolation that segmentation provides is worth establishing clearly here. Segmentation, network segmentation, user segmentation, tenant segmentation is one of the primary technical mechanisms for enforcing the principle. But the principle is broader than any single technical implementation. It is an architectural posture that asks, at every design decision, whether the isolation between users, processes, and tenants is as complete as the system's function requires, and whether the shared components that remain have been identified, cataloged, and hardened. The tension that this principle creates is real, and it is present in every practical implementation. Isolation costs money. Shared infrastructure is cheaper to build, cheaper to operate, cheaper to maintain, and easier to manage from a configuration consistency standpoint. A database server shared by 20 applications is more cost-efficient than 20 dedicated database servers. A unified authentication service shared by every application in the organization is more maintainable than 20 separate authentication implementations. A flat network where every server can reach every other server is easier to troubleshoot than a segmented network with 100 firewall rules. The pressure towards sharing is not irrationality. It is the entirely legitimate optimization pressure that organizations operate under every day. The principle does not say that this pressure should be ignored. It says that the security cost of each shared mechanism should be explicitly understood and explicitly accepted. The organization that runs 20 applications off one database server should know what it is accepting. A database compromise is a 20 application compromise. The organization that runs a shared authentication service should know that it is creating a single point of failure and a single point of attack for every application that depends on it. Understanding the cost is what allows the organization to make the risk worthwhile by investing appropriately in hardening, monitoring, and recovery planning for the shared components that remain. The architecture of isolation, 3 layers where sharing lives. Least common mechanism becomes operational when you can see where in a system sharing is occurring, at what layer, and with what consequence. 3 layers account for the majority of the pivot points that attackers actually exploit. the network layer, the identity layer, and the compute layer. At the network layer, the shared mechanism is the network itself, or, more precisely, the degree to which different users, applications, and trust zones share the same network fabric without barriers between them. A flat network is the extreme case. Every device on the same subnet. Every subnet reachable from every other subnet. Every server able to initiate a connection to every other server. The network is a completely shared mechanism. An attacker who compromises any device on the network has network layer access to every other device, constrained only by whatever host-based controls are running on the individual targets. Network segmentation is the architectural response, the physical or logical division of the network into segments, using VLANs, routing policies, and inter-segment firewall rules, reduces the scope of the shared mechanism by creating boundaries that traffic must cross deliberately through defined and controlled paths. The guest Wi-Fi network and the corporate LAN sharing the same network infrastructure is a design that violates least common mechanism. An attacker on the guest network, or a device on the guest network that has been compromised, has the same infrastructure layer access to the corporate LAN as a compromised corporate device would have. Isolating the guest network through a dedicated VLAN with firewall rules that deny all inbound traffic from the guest segment to the corporate segment means that the network infrastructure is no longer a shared mechanism between guest and corporate users. Gaining access to the guest network does not give the attacker network layer proximity to corporate resources. Microsegmentation extends this logic to its logical limit inside the corporate network. Rather than segmenting at the subnet level, where all servers in the production subnet share a network mechanism with each other, microsegmentation applies east-west traffic filtering at the individual workload level, using host-based firewalls or software-defined networking policies enforced by the hypervisor or container orchestrator. Two servers in the same subnet, running services that have no reason to communicate with each other, cannot communicate with each other. The network is no longer shared between workloads that do not need to share it. An attacker who compromises one server cannot initiate connections to any other server in the subnet without crossing a policy enforcement point. At the identity layer, the shared mechanism is the authentication and authorization infrastructure. The most common expression of this in enterprise environments is a directory service, Active Directory being the dominant example, that serves as the source of identity for every application, every server, every network device, and every user in the organization. This is a single shared mechanism for identity. Its compromise is not a single application compromise. It is an organization-wide compromise, because every system that relies on that directory for authentication decisions now has an adversary sitting in its trust chain. The design response at the identity layer is not to eliminate the shared directory. Eliminating centralized identity management would introduce worse problems, but to implement boundaries within it and to minimize what the shared components can reach. Dedicated service accounts that are scoped to a single service and cannot authenticate to anything else mean that compromising one service's account does not grant the attacker credentials that work against other services. Privilege separation between the administrative tier that manages identity infrastructure and the operational tier that uses it means that compromising an operational account does not give the attacker the ability to create new accounts, modify group memberships, or alter authentication policies. The Kerberos delegation settings in an Active Directory environment are a specific and often under-examined expression of this. Unconstrained delegation, where a service account can impersonate any user to any other service, is a maximally shared mechanism. Constrained delegation, where a service account can only impersonate users to a specific set of named services, reduces the scope of the sharing to exactly what the service needs. At the compute layer, the shared mechanism is the operating system kernel, the hypervisor, or the container runtime that different workloads use as their platform. A physical server running multiple virtual machines shares the hypervisor between all of them. A Kubernetes cluster running multiple containerized applications shares the container runtime and, more significantly, the host OS kernel between all containers on the same node. A shared hosting environment running multiple customer web applications on the same PHP process shares the runtime interpreter between all of them. The security consequence at each of these layers is different in specifics, but identical in structure. The hypervisor, the kernel, the runtime, each is a common mechanism. A vulnerability in that mechanism is a vulnerability that every workload sharing it must inherit. The Spectre and Meltdown vulnerabilities disclosed in 2018 were kernel and microarchitectural vulnerabilities that allowed one process to read memory belonging to another process that shared the same physical CPU. On a shared cloud host, where thousands of customers' virtual machines run on the same physical hardware, these vulnerabilities meant that a malicious customer could potentially read memory belonging to another customer without ever attacking the customer's application, because the attack was against the common mechanism, the shared CPU cache, rather than against the application itself. Mitigating Spectre required a change to how the shared mechanism, the CPU's speculative execution pipeline, was used, specifically the flushing of branch predictor state on every context switch between processes from different trust domains. The compute layer response to least common mechanism ranges from container isolation improvements, using a sandbox runtime like gvisor that interposes a user space kernel between the container and the host OS kernel, reducing the shared surface area, through to dedicated hosts, where a customer's virtual machines run on physical hardware that is not shared with any other customer's workloads. The dedicated host eliminates the compute layer sharing entirely at the cost of density efficiency. The tools that enforce isolation. 4 tools deserve examination not just for what protection they provide, but for what their deployment costs and what they leave exposed. Virtual private clouds, in the context of public cloud infrastructure, are the network isolation primitive that prevents different customers, teams, or applications from sharing network infrastructure. In a cloud environment without VPC boundaries, all traffic within the cloud provider's infrastructure could theoretically be accessible across tenants, constrained only by the routing policies of the underlying network. A VPC creates a logically isolated network segment within which the customer controls the address space, the routing tables, the internet gateways, and the access control lists that govern what traffic enters or leaves. Different applications or different customers placed in different VPCs cannot reach each other's resources without explicit peering configurations. The network infrastructure is no longer a shared mechanism between them. The cost of VPC architecture is operational complexity. An organization that moves from a flat network to a VPC per application model must now manage the peering relationships between VPCs when applications need to communicate The transit gateway or hub architecture that allows centralized services, shared DNS resolvers, patch management systems, monitoring agents, to reach into multiple VPCs without creating a flat shared network. And the security group and network ACL rules that govern what traffic is permitted across those peering connections. Each VPC creates a new trust boundary, and every trust boundary requires explicit configuration. What VPCs cannot address is the sharing at the hypervisor level. Workloads in different VPCs may still share physical hosts and, therefore, share the compute common mechanism unless dedicated host configurations are explicitly requested. Virtualization and containerization provide compute layer isolation between workloads that would otherwise share an operating system directly. A hypervisor allows multiple operating systems to run on the same physical host without seeing each other's memory, file systems, or process space. The isolation boundary is the virtual machine. Each VM has its own virtual memory map, its own virtual disk, its own virtual network interface. A container, by contrast, shares the host OS kernel with all other containers on the same host, but the container runtime isolates the file system, process namespace, network namespace, and user namespace of each container from every other. The isolation is partial. The common mechanism is reduced, but not eliminated. The host kernel is still shared, which means that a kernel vulnerability is a vulnerability in every container on that host. The cost of virtualization is the performance overhead of the hypervisor layer, the operational complexity of managing VM images, and the density reduction of running full operating systems rather than just the application and its dependencies. The limitation is precisely the one identified above. The hypervisor is itself a common mechanism, and hypervisor vulnerabilities, VM escape vulnerabilities, are among the highest severity findings in cloud security research because their impact is not limited to a single VM. Containerization addresses the density problem but introduces a different isolation profile: stronger process-level isolation, weaker kernel-level isolation. Dedicated service accounts apply the principle to the identity layer. The design decision to run every application service as a unique, independently provisioned identity, rather than sharing a common service account across multiple services for operational convenience, means that the compromise of one service's credentials does not provide lateral movement capability to any other service. A database administration credential that is used only for database administration cannot be replayed against the application server, the file server, or any other service, because it was never provisioned access to those services. The account is not a common mechanism shared across the infrastructure. The cost of dedicated service accounts is the administrative overhead of provisioning, maintaining, and rotating a larger number of credentials. An organization that runs 30 services and uses 3 shared service accounts has 30 services to worry about, but only 3 credentials to manage. An organization that implements a dedicated service account per service has 30 credentials to manage, 30 rotation schedules to maintain, and 30 access reviews to conduct. The limitation is the management capacity problem. Without automated credential rotation and secrets management tooling, the operational overhead of dedicated service accounts creates pressure toward credential reuse or static long-lived credentials, both of which negate the isolation benefit. The security win from isolation must be accompanied by the operational investment in automation or it will not be sustained. Microsegmentation enforces the isolation that VLANs, and subnet-level segmentation cannot. Traditional network segmentation operates at the boundary between subnets. Traffic flowing from one subnet to another crosses a firewall or routing policy. But within a subnet, all devices share the same network mechanism and can initiate connections to each other without crossing a control point. An application server and a database server in the same production subnet can communicate freely, which is necessary for the application to work, but so can the application server and the backup server, and the backup server and a developer's jump host, and so on. Microsegmentation moves the control point from the subnet boundary to the individual workload, implementing allow list policies that specify exactly which workloads can communicate with exactly which other workloads on which ports. The shared network mechanism becomes, in effect, a series of isolated bilateral channels, each explicitly permitted. The cost of microsegmentation is the rule-based complexity that comes with fine-grained policies. An environment with 50 servers might require hundreds of microsegmentation rules to accurately reflect its legitimate communication patterns. Those rules must be maintained as the application changes, new microservices added, old services decommissioned, communication patterns updated. A microsegmentation policy that is not kept current with the actual application architecture will either block legitimate traffic, causing availability failures, or accumulate exception rules that progressively erode the isolation. The limitation is the bootstrapping problem. To build an accurate microsegmentation policy, you must have an accurate map of all legitimate communication flows, which requires either extensive traffic observation before policy enforcement or a development process that generates communication flow documentation as a standard artifact of service design. Implementation. Building isolation into the architecture. Two implementation scenarios reveal the practical reality of applying least common mechanism to systems that were not designed with isolation as a primary concern. The first is the design of a three-tier web application architecture: web tier, application tier, and database tier, that enforces the isolation between layers while allowing the legitimate communication that the application requires. The temptation in a three-tier architecture is to place all three tiers on the same subnet, connect them with a single shared security group, and control access at the external boundary. This design treats the three tiers as one shared compute mechanism. A vulnerability in the web tier, a remote code execution flaw in the web server software, for instance, gives the attacker a foothold on a machine that has network layer access to both the application tier and the database tier. The three-tier label is architectural, but the isolation is not real. The correct implementation places each tier in a dedicated subnet within a dedicated security group. The web tier security group permits inbound traffic from the internet on port 443 and inbound traffic from the load balancer's health check addresses and nothing else. It permits outbound traffic to the application tier security group on the specific port the application API listens on and nothing else. The application tier security group permits inbound traffic only from the web tier security group, outbound traffic to the database tier security group on the database port, and inbound traffic from the management plane for deployment and monitoring purposes. The database tier permits inbound traffic only from the application tier security group. No resource in the database tier can be reached from the internet directly, from the web tier directly, or from the management plane except through the specifically defined management path. The additional non-obvious considerations are these. Each tier should run with a dedicated IAM role that grants it access only to the AWS services or GCP services or Azure resources it needs to perform its function. The web tier's role can write to a specific CloudWatch log group and nothing else. The application tier's role can read from a specific S3 bucket and call a specific secrets manager path to retrieve database credentials and nothing else. The database tier has no outbound IAM permissions at all. When the application needs to call an external API, that call is routed through an AT gateway, and the security group of the application tier is configured to permit outbound traffic only to the IP ranges of the external service, not to the entire internet. The governance layer that must accompany this technical architecture is a change management process that requires all new communication flows to be reviewed and explicitly permitted. An architecture that is correctly isolated at deployment but allows any developer to update a security group rule without review will accumulate permissions over time until the isolation is no longer meaningful. The technical isolation and the process that maintains it are inseparable. The second implementation scenario is the challenge of building a managed security services environment where multiple customers' data, alerts, and configurations are handled by the same platform and the same analyst team, while ensuring that one customer's data cannot be seen by or affect another customer's operations. This is the multi-tenancy isolation problem, and it is the operational expression of least common mechanism at the service delivery layer. The first implementation concern is data isolation. Customer log data must be stored in tenant-isolated partitions, separate database schemas, separate object storage buckets, with separate IAM policies, separate encryption keys managed per tenant, such that a misconfiguration in one tenant's data path cannot expose another tenant's data. This means specifically that the application layer's data access logic must enforce tenant context in every query. Every read, every write, every search operation must include a tenant identifier that is validated against the authenticated session, not derived from user-supplied input. A CM platform where the tenant filter is passed as a query parameter that the user can modify is a platform that has not isolated its data mechanism. The database is a common mechanism shared across tenants, with a filter that can be bypassed. The second concern is alert isolation. When a threat intelligence feed identifies a new indicator of compromise, the enrichment of that indicator should be applied to one tenant's alerts and the context derived from that enrichment, including details about the attacker's infrastructure and what other tenants have been targeted, should not be automatically shared across tenants without explicit consent. Intelligence sharing between tenants of an MSSP is sometimes desirable and sometimes prohibited by contract. The platform's default must be isolation, with sharing enabled only through explicit configuration. The common mechanism here is the threat intelligence pipeline. If a single pipeline enriches all tenants' alerts without tenant-level filtering, a detail about one customer's environment may propagate into another customer's alert context. The third concern is incident isolation. When an analyst is working a high-severity incident for one customer, the tools they use, the query interfaces, the playbook automation, the communication channels should enforce that the context of that investigation is not visible to the customer's competitors who are also tenants of the same platform. This requires both access controls in the tool layer and workflow controls in the operational process. The analyst should not be able to query across tenant boundaries, and the case management system should not display tenant identifying information to team members who are not assigned to that tenant's account. When isolation fails, working through three failure scenarios. Three failure scenarios work through how least common mechanism violations surface in practice, what the diagnostic process looks like, and what the fix reveals about the underlying architecture. The first scenario is ransomware that has encrypted file shares across an entire organization's network, with the spread seemingly unstoppable despite the IT team disabling the initial patient zero workstation. The backup restoration attempt fails because the backup system, which was mounted as a shared network drive, was also encrypted. The diagnostic begins with the network architecture. Pull the network topology diagram for the organization. The critical question is not how the ransomware entered. That is a separate investigation. The question is why it spread so far. Ransomware that spreads across file shares is using the file shares as a common mechanism. Every host that had a mapped network drive to the infected share has its own files exposed to encryption. If all workstations in the organization have mapped drives to all shared file servers, the file sharing infrastructure is a single common mechanism that connects every workstation to every other workstation's data. The second diagnostic question is the backup architecture. A backup system that mounts network drives to perform its backup is a backup system that, under ransomware conditions, presents the same mapped drive mechanism that the ransomware is traversing. The ransomware sees the backup destination as another mapped network drive and encrypts it. The backup system should be architected as a pull model rather than a push model. The backup system connects outbound to the sources it is backing up from a network segment that the source workstations cannot reach, and the backups are written to storage that is not accessible from the network segments where the ransomware is operating. The backup storage is not a common mechanism shared with the production environment. The remediation has three time horizons. Immediately, contain the spread by disabling the file sharing service on all servers and isolating the network segment containing the affected systems. In the recovery phase, restore from the last clean backup, which, if the backup architecture was correct, exists on isolated storage, while auditing every restored file share's permission structure. In the redesign phase, implement network segmentation that prevents workstations from reaching file servers they have no legitimate reason to access. Implement microsegmentation between file servers in different departments, and rebuild the backup system as a pull-based architecture with isolated storage that is not reachable from the production network. The second scenario is a cloud environment where a critical RCE vulnerability in a container image was deployed to production despite container image scanning in the CI/CD pipeline. The investigation reveals that the vulnerability was detected, but the pipeline allowed the deployment to proceed because the detection rule was set to warn rather than block on this specific CVE severity level. More concerning, the deployed container was running with a service account that had broad permissions across the cluster, permissions that allowed it to read secrets from every other service's namespace. The diagnostic identifies two distinct violations of least common mechanism. The first is the CI/CD pipeline's role as a gatekeeper that was misconfigured to permit what it should have blocked. This is an enforcement mechanism failure rather than an isolation failure, but it enabled the second violation. The second is the service account scope. A single service account with cluster-wide secret read permissions is a common mechanism shared across every service in the cluster. The compromise of any container running under that account, regardless of which application it belongs to, grants the attacker access to the secrets of every service in the cluster. The root cause analysis should cover the specific pipeline policy configuration. Who set the severity threshold that allowed this CV to pass as a warning? When was the threshold set? Was it intentionally set at that level, or was it misconfigured during a pipeline migration? The service account investigation should map every permission that account holds against the actual permissions needed by the specific service that was compromised. Almost certainly, the account holds permissions far beyond what any individual service needs, accumulated through the convenience of shared service identity rather than a per-service identity. The immediate containment step is to revoke the service account's permissions and rotate all secrets that were readable by that account. The fix for the pipeline is to change the enforcement policy from warn on high to block on high, with a documented exception approval process for cases where a high-severity CV must be accepted temporarily. The fix for the identity architecture is to remove the shared service account and replace it with per-service accounts scoped to exactly the secrets that each service needs, managed through a secrets management system that enforces per-service access controls. The third scenario is a multi-customer MSSP environment where two customers receive alerts for the same indicator of compromise, but the incident tickets created by the automation system assign different severity levels to the two alerts, one high, one medium, without any visible reason for the discrepancy. Both customer security teams push back. The one receiving a medium severity alert for what they believe is a high severity threat, and the one receiving a high severity alert that their own team assessed as medium. The diagnostic begins with the severity assignment logic in the automation. Pull the playbook that handles IOC-based alert generation and trace the inputs to the severity calculation. The severity is likely computed from a combination of the IOC's reputation score, the asset criticality of the affected system, and possibly some contextual enrichment from the threat intelligence platform. The question is whether any step in that pipeline consumes or produces state that is shared across tenants. In this case, the investigation reveals that the threat intelligence enrichment module maintains a global cache of IOC reputation scores. When the first customer's alert triggered the enrichment, the module queried the reputation API, received a high-severity score, and cached that score with a 30-minute TTL. When the second customer's alert triggered enrichment 12 minutes later, the module retrieved the cached score. But between the first and second enrichment, the reputation API had updated its dataset based on new analysis that revised the IOC's severity downward. The first customer received the pre-update score. The second customer's cache hit returned the pre-update score as well, not the updated one. The cache was shared across tenants, and the cache state from one tenant's enrichment was being served to another tenant's request. The root cause is a shared enrichment cache that was implemented for performance reasons without considering the tenant isolation implications. The cache key was the IOC hash, without a tenant identifier component. The fix is to either make the cache tenant scoped. Each tenant's enrichment results are cached independently, so one tenant's cache state cannot affect another's, or to document that the enrichment cache is a known common mechanism with a defined TTL and accept that alerts for the same IOC within the cache window may show the same reputation score regardless of any API updates in between. The latter is acceptable only if the TTL is short enough that the staleness risk is understood and agreed to. The standardization of the severity process should also ensure that the severity calculation logic is identical for all tenants, with the only variation being customer-specific asset criticality data, not shared enrichment state. 3 roles, 3 isolation problems. A security architect, a SOC analyst, and an MSSP analyst each encounter least common mechanism at a genuinely different layer of the problem, and each role's effectiveness depends on a different mode of reasoning about shared components. The security architect's defining moment is the design review for a new OT environment where the business has decided to connect industrial control systems to the corporate IT network for operational reporting purposes. The reporting requirement is real and the business case is legitimate. Plant managers need real-time data on production metrics, and the easiest way to provide that data is to put the SCADA systems on the same network as the reporting tools that consume the data. The architect sits with this requirement and sees the common mechanism problem with precise clarity. The corporate IT network is a mechanism shared with the plant automation network, and any IT security incident that gives an attacker network access to the corporate environment now potentially gives them network access to the systems that control physical production processes. Safety-critical systems should not share a network mechanism with systems that are subject to commodity IT attacks. The architect response is an industrial DMZ, a dedicated network zone that sits between the IT network and the OT network and serves as the integration layer. The DMZ hosts the data historian, the reporting server, and the integration middleware. Data flows from OT to the DMZ in one direction, using a data diode or a unidirectional security gateway that physically prevents reverse traffic. Data flows from the DMZ to IT reporting tools in the other direction through a firewall with application-level inspection. The OT network and the IT network never share a network mechanism. The DMZ is the carefully designed, explicitly secured integration point, not a shared mechanism, but a controlled bridge. The architect documents this design decision, the threat model that motivated it, and the specific controls that enforce the isolation, because the design must be understood by everyone who operates and modifies it after the architect is gone. The SOC analyst at L2 or L3 encounters least common mechanism in the investigation of anomalous traffic from an internal host to a known command and control server on port 443. The initial triage looks like a single compromised host. But the analyst who understands lateral movement through shared infrastructure asks a different set of questions before concluding that the scope is limited to one machine. What network segment is the affected host in? Which other hosts share that segment? And can they reach each other? What services does this host share with others? Shared drives, shared printers, shared authentication servers. Is the host running any services that other hosts depend on? A local DNS resolver, a software distribution server, a jump host for administrators? The common mechanisms that connect this host to the rest of the environment are the attack surface for lateral movement. The analyst pulls the network flow log for the affected host's outbound connections over the previous 72 hours, specifically looking for connections to other internal hosts that are unusual in protocol, port, or timing. They query the authentication logs for credentials that authenticated from this host to other systems in the period since the first C2 beacon. They check whether the host is a member of any privileged groups in the directory service that would make its credentials useful against high-value targets. The investigation is not just about what the attacker has done with this host. It is about what the shared mechanisms connecting this host to the rest of the environment allow the attacker to do next, and whether those mechanisms have already been used. The MSSP analyst's version of this problem is the multi-tenant alert, where two customers receive notifications about the same campaign, and the analyst must communicate about each customer's exposure without allowing information about one customer's environment to appear in the other's case file or communications. The analyst understands that the threat intelligence platform, the case management system, and the communication channels are all shared mechanisms across the customer base, and that information management in a multi-tenant environment requires the same discipline that a physical security analyst would apply to documents labeled with different compartment markings. The analyst creates separate case files for each customer in the case management system, with tenant-level access controls that prevent cross-tenant visibility. The threat intelligence context they communicate to each customer is scoped to what is relevant to that customer's environment. The analyst knows which other customers were hit by the same campaign, but that information is shared only with the affected customers through channels that are scoped to each customer. If both customers need to understand that this campaign is industry-wide, the analyst communicates the industry context without revealing customer-specific details about either. The discipline of information compartmentalization in a multi-tenant environment is not a bureaucratic overhead. It is the operational expression of the principle that the shared intelligence infrastructure should not become a mechanism through which one customer's exposure details flow to another. Case scenario: 50 tenants, 1 physical host, 1 vulnerability. You are the principal security architect at a cloud service provider that hosts 100 enterprise customers on a shared infrastructure platform. The customers span financial services, healthcare, government contractors, and retail. 14 of them are regulated under frameworks that impose strict data isolation requirements, PCI DSS, HIPAA, and several national government cloud compliance regimes. At 3 in the morning on a Tuesday, a security research team publishes a side-channel vulnerability affecting Intel processors that are the exact generation used in your primary data center. The vulnerability allows a process running in one virtual machine to read memory from a neighboring virtual machine on the same physical host by exploiting patterns in the shared L3 cache. The exploit requires local execution in the attacker's VM, which means any customer who can spin up a virtual machine on your platform can potentially use this exploit. The attacker does not need to compromise your infrastructure. They need to be a customer. The constraint that shapes every decision you make in the next 72 hours is this: you cannot take the entire platform offline. 2 of your customers are healthcare systems running patient monitoring applications that operate continuously. 3 are financial institutions whose trading systems must be available during market hours. 1 is a government emergency services coordination platform. The business continuity requirement is not optional. Your first action in the first 2 hours is classification. You pull the host allocation table for every physical server in the affected hardware generation and categorize every running workload by customer and by regulatory classification. The question you're answering is: which physical hosts have mixed tenant workloads where a regulated, high-sensitivity customer shares a CPU with any other customer? Of your 14 regulated customers, 11 are currently co-located on mixed-tenant hosts with other customers. 3, by coincidence of capacity planning, happen to be on hosts that are exclusively allocated to their workloads. The 11 mixed tenant placements are your immediate problem. The 3 regulated customers on single-tenant hardware are safe from the published exploit because the common mechanism, the shared CPU and L3 cache, does not exist in their case. They share nothing with another customer's workloads at the compute layer. For the 11, you initiate a live migration of their workloads to dedicated host hardware. Your cloud platform's orchestration layer supports live migration without service interruption for most workload types. A virtual machine can be moved from one physical host to another while it is running, with a brief network handoff that is transparent to the application. You execute these migrations in order of regulatory sensitivity. The government workloads first, the HIPAA-covered healthcare workloads second, the PCI DSS financial workloads third. Each migration takes the affected customer's workload from a shared physical host to a dedicated physical host where no other customer's workloads run. The common mechanism, the shared CPU, is eliminated for these customers. The remaining 86 customers are on mixed tenant hosts with varying co-tenants. For these customers, you implement microarchitectural mitigations, the operating system update that flushes branch predictor state on context switches between VMs from different customers, a mitigation that substantially reduces the exploitability of the vulnerability at the cost of a measurable performance penalty in your environment. The benchmark shows an 8 to 12% latency increase on workloads that are sensitive to context switch overhead. You make the decision that this performance penalty is acceptable as a temporary measure while permanent hardware isolation is planned. The communication to customers follows a tiered structure. The 11 regulated customers whose workloads were migrated to dedicated hosts receive direct notification within 6 hours of the migration. A brief technical explanation of the vulnerability, a description of what was done on their behalf, confirmation that their workloads are now on dedicated hardware, and an invitation to a security briefing where their questions can be answered. The remaining 86 customers receive a general security advisory about the vulnerability and the operating system mitigations applied, with a technical summary of the residual risk and an offer to discuss dedicated hosting options. 3 customers whose workloads fall into the general advisory category escalate to their legal teams, who send requests for written assurance about data isolation. You prepare a response that distinguishes between the microarchitectural isolation provided by the deployed mitigations and the physical isolation provided by dedicated hosting, and that offers the customers the option to migrate to dedicated hosts at the cost differential that reflects the lower density of exclusive hardware allocation. 2 of the 3 accept the cost differential and request migration. The third accepts the written assurance after their legal team reviews the technical description of the mitigations. The post-incident review, conducted 3 weeks later, identifies 2 systemic issues in the architecture. The first is that dedicated host allocation was not a default option in your onboarding process. It was an available but explicitly requested and priced option that most customers declined during procurement because the cost delta was not explained in terms of the isolation benefit it provided. The technical default was shared hosting, which is also the default that maximizes the number of common mechanisms in the platform. The recommendation from the review is to restructure the onboarding conversation so that customers who have regulatory isolation requirements are identified at onboarding and automatically placed on dedicated hosting, with the cost reflected in their tier rather than as an add-on that can be declined. The second finding is that the host allocation table, the record of which customer workloads are running on which physical hosts, was not queryable in real time during the incident response. The team had to assemble the classification manually from several data sources, which took 2 of the 6 hours available before the exploit details became widely known. The recommendation is to build a continuously maintained, queryable host allocation database that includes customer regulatory classification, workload sensitivity, and current physical host assignment, so that in any future incident requiring rapid triage of co-tenancy risk, The classification can be completed in minutes rather than hours. The outcome of the incident is that the 11 regulated customers sustained no exposure because the common mechanism, the shared CPU, was eliminated before the vulnerability became exploitable. The 86 general customers sustained reduced but non-zero residual risk from the period before the microarchitectural mitigations were applied, a window of approximately 4 hours between the public disclosure and the completion of the OS updates across the fleet. No customer reported evidence of actual exploitation during that window. 2 customers whose contracts included incident notification obligations received formal notification within the contractually specified time frame. What the incident revealed, stated as a principle, is that isolation is not a feature that can be added at the time it is needed. The 3 regulated customers who were already on dedicated hosts before the vulnerability was published were not on dedicated hosts because someone anticipated this specific attack. They were on dedicated hosts because a previous architecture review had identified compute layer sharing as a risk that their regulatory environment did not permit, and the isolation was built in at the design stage. The isolation was present before the attacker arrived. That is the only form of isolation that can be trusted. Closing. The art of deliberately choosing what to share. The mental habit that this principle builds is the habit of stopping at every design decision to ask a question that is easy to skip. Does this component need to serve more than one user, process, or tenant? Not whether it can, not whether sharing is technically possible, not whether sharing is efficient, but whether the isolation that sharing forecloses is something you're willing to accept the cost of losing. Efficiency will always argue for sharing. A shared authentication service is cheaper than 12 separate ones. A shared database is simpler to operate than a dozen dedicated instances. A flat network is easier to troubleshoot than a segmented one. These arguments are not wrong. They are incomplete. They account for the operational cost of isolation and stop there without accounting for the security cost of the common mechanism that sharing creates. The organization that applies least common mechanism well is the one that knows exactly which components it has deliberately chosen to share, why it made each choice, what additional controls it has applied to harden each shared component, and what its recovery plan looks like if any shared component is compromised. That is a very different posture from the organization that shares components because sharing was the default, has never enumerated what it has shared, and discovers its common mechanisms for the first time when an attacker traverses one. Security is not about eliminating sharing. It is about making sharing a conscious decision rather than an accidental accumulation. The boiler room in the apartment building is not inherently dangerous. It is dangerous when a utility infrastructure radiating from it was designed by someone who only thought about connectivity and efficiency and never stopped to ask, who else does this component reach? And what happens if it is compromised? Ask that question. Document the answer. Build the isolation that the answer demands, and monitor the shared components that remain. End of session. Least common mechanism. Minimize shared components.